Okay, our final topic in Math 418 is going to be queuing theory. So what we've talked about so far in this semester, if you think back to the very beginning, we started with uh, discrete deterministic models. So discrete models where the outcome was fixed, right? We always knew exactly what the next step was going to be. And then we did discrete stochastic models where we introduced random behavior into our discrete models. Okay. Then we did our empirical models. That led us into continuous models. Um, but they were deterministic continuous models, right? So the behavior was fixed, but they were continuous. Now we're going to finish up by talking about stochastic continuous models. So continuous models where there's some sort of random behavior involved. Now, we're not going to go super deep into these because they do get very complicated. They use a lot of statistics. We'll talk some more about some of these in statistics in Math 313, or if you've seen them there. But we are going to talk about some of them just so you can get a feel for kind of what these models are like. Okay? And so what we're going to talk about is the idea of what's called queuing theory. So queuing theory is the study of how people behave in lines. So, for example, if you think about different places where you have to line up to do things, for example, if you go to the supermarket, there are times when there's nobody in line and you just walk right up and check out, or there are times when there are lots of people in line. There are times where they have one supermarket register open and times when they've got 10 open, right? And so, how do you make the decision of how many lines do you have open? How many people should you have? That's what queuing theory studies, is that kind of idea. Okay? And why are some places so much more successful in how they manage their lines? So, for example, fast food restaurants have tremendous ways of dealing with queuing theory. How do they decide whether a restaurant should have two fat drive-throughs? Things like that. Okay? So that's all queuing theory. So the simplest way to approach this would be with a deterministic model. Okay? So say customers show up at a rate of A per minute and are served at a rate of S per minute. Okay? So say, for example, A is 3, S is 5. So 3 people show up to your store every minute, but you can serve 5 people every minute, and so you never get a line, right? So if you think about this, every 1 over A minutes, someone arrives. Every 1 over S minutes, someone leaves. Okay, because they're done, they've been served. And so if 1 over A is greater than 1 over S, right? So if you get less people every minute than you can serve, then you're fine, right? If 1 over A is less than S, in which case A is greater than S, then you're in trouble, right? You're getting more people arriving every minute than you can serve, and you get into trouble, right? And so if A is greater than S, greater than or equal to S, a line forms of length A over T minus S over T, right? So A times T, rather, would be the number of people that have arrived at time t. S times t is the number of people that you've served by time t. And so if A is larger than S, AT minus ST is going to be positive, and you get a line with that length. Okay? And it grows at a rate, of course, the derivative of this is A minus S people per minute. Okay? So this is a terrible model for a line. Okay? So if you think about this, none of this is true to the real world, right? Unless your Q, your line, is an assembly line in a factory, right? Or all of your customers are robots that arrive with precision every so many units of time. This is not how this works, right? You don't always get A people per minute. You get some sort of random distribution of people. Maybe A is the average number of customers you get per minute, but that's not exactly what you're going to get, okay? And so the solution to really understanding a Q is to think about probability and think about a random stochastic model, okay? And so we're going to build this up in sections. The first thing that we're going to look at is a model for one customer, okay? So, and then we're going to use that to build up our whole thing, okay? So if you think about one customer, we're going to have that the probability that a customer is served every unit of time. So is served in delta t units of time is mu delta t. Okay, so mu is just some constant. And so if you think about the probability that you finish your business, that you get served in a minute, should be 1/10 of the probability that you finish your business in 10 minutes. And so that's why we take this mu times delta t, right? So if delta t is 1 minute, it's just going to be mu. If it's 10 minutes, it's going to be 10 times mu. You're that much more likely to have finished, okay? And so we have two states here, and we have a very simple Markov chain, okay? So if you're in line, you're being served, or you're done, right? So our one customer is either being served or they're done. Each delta t, there's a probability mu delta t that they move from being served to done. And the probability that they stay in being served is 1 minus mu delta t. And then, of course, once they're done, they stay done. This is an absorbing state, and so the arrow out of it is just 1. Okay? So this is a very simple model, right? One single customer. It's a Markov chain, and it has a very simple kind of structure, right? So if you write down the recurrence relations, you can write down recurrence relations for what the probability is that a customer is in either of these states at a particular time, right? So remember, in a Markov chain, all of our terms represent probabilities. And so if you want the probability of t plus delta t, so P is going to be the probability that somebody is still being served. Q is the probability that they're done. So still served versus done. Okay? And so P of t plus delta t, Q of t plus delta t is just going to be these probabilities, right? So the probability that somebody who is being served stays in that state is 1 minus mu delta t. The probability that somebody who's being served moves into the done state is mu delta t. That's going to go down here. Probability that somebody who is done moves into the being served state is 0, right? Nobody goes from being done to being back in line. And then the probability that somebody who's in the done state stays there is 1. Okay? And so what you do is you take this matrix times those probabilities, and so this gets you recurrence relations. So something like, if you work out what these are, P of t plus delta t is equal to 1 minus mu delta t times P of t. Okay, so the probability that you're still being served is 1 times mu of delta t times the previous probability. And if you work this out, P of t plus delta t equals P of t minus mu delta t P of t. Move the P of t over to the other side. P of t plus delta t minus P of t equals negative mu delta t P of t. And then what I'm going to do is divide through by delta t. So P of t plus delta t minus P of t over delta t equals negative mu P of t. Okay? And so delta t here is just a unit of time, right? This is a discrete unit of time. If we want to make this continuous, what we want to do is we want to make delta t smaller and smaller and smaller, right? Because rather than having like 1 unit between each of our time steps, we want to have an infinitesimal between each of our time steps to make it continuous. So we're going to take the limit as delta t goes to 0 of both sides, though of course if you take it on this side it doesn't change anything because there's no delta t over here. And of course the limit as delta t goes to 0 of P of t plus delta t minus P of t over delta t. You should see here hiding, this is the derivative. P prime of t equals negative mu P of t. And so we get this as a differential equation. So P prime equals negative a constant times P. You should recognize this. This is the differential equation for the exponential equation. And so for a single customer, the probability that they're still in line, if you solve this, is some P0 e to the negative mu t. Okay? And so P0 is the probability that they are in that state in the first place, right? And so what we see is that the probability that they stay in the being served state decays exponentially, okay? So this is called an exponential distribution. And so if you know any statistics, you can do a little bit of work with this. And what you can find is, and this shouldn't be a surprise, the average wait time what's called the expected value of this distribution. So if you're interested in it, what it is it's the integral of t times this function from 0 to infinity. And what that is, that's the expected value. The average wait time is 1 over mu, okay? And so if you think about it, if you've got a 1 out of 2 probability, right? So say mu is 1 out of 2 of being served each minute, well, then you would expect to wait 1 over that. So 1 divided by 1/2 would be 2. If you've got a 1 out of 2 chance of being served every minute, then you would expect to wait an average of 2 minutes. Right? Now, it's stochastic. You might wait less than that or more than that, but that's what you would expect So the average wait time is 1 over mu. Okay? In the next video, so now we figured out what happens with one person, right? How it's distributed. In the next video, we're going to look at multiple people standing in the same line and see how that works.